We're here today. We're going to be talking about constructability for designers. Basic concept for this presentation is in a design guide, Design Guide 23, published early last year by AISC. It follows a process in here that's somewhat more. This is not a guide showing you simple connections versus difficult connections. Doesn't indicate use 3/4 inch bolts versus 1 inch bolts. It really talks about the possibility of and the information that construction knowledge and experience needs to be infused into the design process. And so we've broken up the presentations. We had a primer a little earlier. This one is going to be focused on the designer. Some of the things we believe you need to know, things that you should be looking to include in your design decision matrix. Probably elements that you have not considered putting them there because they may appear to be means and methods, but we will talk about that. But you're looking for a magic number, and that magic number is S as in Sam, G as in George. 79K. SG 79K. That will be the digit number that you put in to get your PDHs. So let me introduce myself. I'm Dave Ruby, Chairman and Founding Principal of Ruby & Associates. We are a consulting structural engineering firm out of Detroit, and our primary clients are contractors and owners. We do consulting work with architects, but primarily we're on the contracting end of the business. We do erection procedures, installation procedures, stability analysis, long span structures, fabrication techniques, welding procedures, welding joints, design, detail joints, anything and everything that has to do with structural steel. That's certainly our strength. We also do foundation design and we do some concrete work, but primarily my experience is 10 years with American Bridge and some 8 years with a design build firm. And so I was born and raised in western Pennsylvania, and when I get cut, I don't bleed, I rust. So I would say that's what my background is. That's where I am. Steel is what I've inhaled all my life, and so now I'm exhaling. We'll have another speaker, and I will introduce him when it's time, when we get through. So I thank you for being here today. Can you see the screen well enough in the back? Do I need to lower the lights? Is it okay? All right? Is it fine? All right. Good. Thank you. The other speaker will be Chad Fox. He's a project engineer with my organization. He's been 8 years of experience, has a bachelor's from Michigan Tech and a master's from Purdue. He's licensed as a professional engineer in Michigan, as a structural engineer in Illinois. We basically, the firm, are attempting to encourage our individuals to become registered as PE, certainly in Michigan, but we're looking for them to get a further registration, and we have chosen either California or Illinois for what we want them to proceed in. So Chad will talk about some of the case studies and projects we've been involved in. So let me get started, if I might. We're going to try to introduce today constructability, and as a design philosophy, basically as a continuous process in the design. Not something that happens at 50% documents or at 90% documents or prior to putting out the bid documents, but something that happens along the way, continuously. We're going to review portions of the design guide, and we're going to discuss a few case studies. We would like you to interrupt. In fact, if you have a question along the way, please, interruption is not an issue. We will try to get done in time and have time for questions afterwards, but if the force moves you at that point in time, feel free. As I said, the design guide is from the AISC, is published, and basically we talk about the Constructability Institute and where we got the idea, or excuse me, where we picked up the concept of this is that the Constructability Institute in '89, after studying many projects within the private and the public sector, came up with a concept of constructability, meaning the optimum use of construction knowledge and experience in the planning, design, procurement, and field operations. And what takes place presently under most construction operations is that the only time construction knowledge and experience gets involved is during the bidding stage and then the subsequent field operation. And we're indicating that within the design decision matrix, elements at the site can in fact impact the way you design your project. In addition to that, the availability of material, availability of labor, availability of local skills, all of that should impact what you're doing. We know that in Texas, structures tend to be concrete. If we go further north, they tend to be steel. We like to think that concrete core walls make a very nice, neat lateral system and make it a little easier to design the whole process. But in fact, depending on where are you in the country, that doesn't work out too well. It becomes a schedule issue with regard to installation. There isn't the quality or the talent equal in various areas. In particular, in our area in Michigan, concrete cores are an encumbrance to a project. I would tell you that constructability, what it is not what I consider to be value engineering, which we do a lot of, because that takes place at a finite time, likely just at the time when the project as bid comes out. At that period in time, the schedule has already been set. Everybody's confirmed in their mind as to what will take place and what can take place. And they're obviously, in their minds, there's not enough time to do value engineering. But in addition to that, what we're saying is constructability is more than that. It's also not means and methods. It has aspects of means and methods, but it is not that concept. It also is not the constructability reviews, which if any of you have ever searched on the web for constructability reviews, there's 10, 15, 20 firms that perform those for you. They will review the documents at 30, at 60, at 90%, provide reviews, give critiques, etc. with regard to it. But I'm saying in that process, what has happened and what is difficult to do in that type of process is to come back and say your basic structural system is not correct for the site or for the location or for the locale or for the labor or for the equipment. It's too late to do that. What I believe and what we're indicating and the process we're talking about is that constructability is a continuous process and it's not an event. It takes place throughout. There is input from construction and experience that can take and impact decisions all along the way that will improve schedule, improve costs, improve image, reduce RFIs, reduce claims, reduce liability, increase profitability, all along the way. But in your process, if in fact your organization as a designer tends to do this or wishes to consider doing this, what needs to take place is, first off, senior management must be committed to the process and the concept. What that amounts to is the fact that they, in fact, are going to address that. They will be looking to bring that process into the design, and it becomes part of your generation of your design decision matrix. You will need to do a very strange thing from the design issue, but you are going to invite the fox into the hen house. You're going to try to have a collaborative and integrated design environment. Now, this particular number 2, it's probably easier for me to say it than it is to do it. As a general rule, we are primarily creatures of the design, bid, build environment. And the design, bid, build environment functions under the fact that as a designer, you generate designs, and then they are bid on the outside for the contractors, and the low bid is chosen. Well, what's the low bidder mean? That means he forgot something, he misinterpreted something, he saw something on the drawings that wasn't really clear, and so he chose to not include that and argue about it later. Okay. So what we end up then with is an adversarial relationship between the designer and the contractor, because the designer has the feeling that the contractor is setting him up, and the contractor has the feeling that the engineer has no idea how to build this building, so what they've shown on the documents is their cartoons out of their model. So you end up walking into that first meeting trying to defend yourselves. They're going to defend their price, you're going to defend your design. That environment is where we are. That's what makes design build a question as to whether it can really function, because we're asking contractors and designers to be together, and you're not naturally born to do that. You haven't been trained to do that. If we go to IPD, which some of you have probably read about and seen, it seems to be the latest flavor of Jell-O on the market. We are really collaborating there. What they're going to do is have you sign a contract, and everybody signs the contract. So now you're all free. There's no claims because you sign a contract. You're not going to claim. You all are going to collaborate because we're going to tell you to collaborate. Okay? That's like taking the kids on your street and say, okay, you are all going to play, and you're all going to have a good time, and no one's going to argue. And we know that's dreaming. So I agree, and I will tell you that that is difficult. But there has to be confidence here if you ever hope to do any collaborative or integrated design process. We talk about encouraging teamwork. We're talking about leadership and communication skills, and the ability to communicate, the ability to present an argument but not be disagreeable, the way to present a concept for discussion, a way to, in fact, when you're in communication skills, I would suppose one of the things we tend to do, it just happens by human nature, we tend to defend our own turf. So we're in a brainstorming session, and someone generates a little strange idea coming off the first one, and what's the first reaction? Somebody's going to tell them why it doesn't work. Well, then number 2 says something, and he's going to tell them it doesn't work. So do you think you're going to get number 3 or 4 or 5? You're not going to get those ideas. Well, statistically, what I will tell you is that somewhere, if you do a brainstorming session, do as many as you would like, somewhere between the 3rd idea and the 5th idea will be the best idea. So I would submit that in most design offices, when you make your decision with regard to the framing or the type of connections you're using or the lateral system, or whether it's a mix of concrete or steel or concrete or masonry and steel or whatever it might be with timber, that you do not go through 4 or 5 or 6 options or alternatives, because you come there with a preconceived notion about what it's going to be, and you're moving in that direction, and then you'll spend the rest of the time defending that. Okay? And what I'm indicating is I think there's room for discussion. There are things that you don't know. Constructability also includes early involvement in the concept and development and continues through construction and design. What I'm saying is I don't invite the gentleman in at the beginning and ask him, okay, should this be steel or concrete? He says it's concrete, then he leaves, and then we just proceed ahead. The scenario would be all the way along the line, all of our decisions need to be tested. None of them are ever put on a hook and nailed there. They're all pliable through that process. Constructability is a major element of the design process, this inclusion of construction knowledge and experience. The internal constructability reviews, code checks, and document coordination are performed on a regular basis. So what it amounts to is somewhat like your post-job audits, that in this process, in order to get it so that everyone is thinking this way, that you take time, maybe, depending on the size of the project, maybe once a month, that you take a couple hours and just review where we are and how we got here, what were the decisions, are we still on vision, so we proceed ahead. We can evaluate, and then one of the major things is we've got to provide feedback. And the owner needs to be involved in this, by the way. So within this process, I'm talking about evaluating the client and the team's needs and really understanding those needs. But we're going to be reviewing and looking at the site, and we're looking at the preliminary design. But why are we looking at the site? As a designer, does the site make a difference? You got the soil report, tells you where the foundations need to be, tells you what your conditions have to be. The architect has cited the structure, and you're designing it. So why is it the site review of importance? Well, some of the things we might consider would be is there access for us to bring and load equipment in? Is there a laydown area? Is there a pre-assembly area? Is there stock area? Is there room for trucks in and out? Is there room for the crane? Are they going to be crawler cranes? Are they going to be tower cranes? Are they going to have a luffer? Not a luffer? All of those elements impact the cost of what gets done and can impact the structural system that you choose to do. For instance, if in fact you're going to erect the structure because of where it's sited off the back of a truck, then it's going to be very difficult to install 120-foot trusses up at the 10th floor across the ballroom in that structure. And what will have to happen is those trusses will come in pieces and be assembled on the floor up there somewhere. So then the question is, well, will your floor take that assembly loading? Now, is that a design issue? I would submit it's a cost issue. It's a schedule issue on the project. And you, as an individual, do have a major impact on that cost and construction. So I'm not suggesting that you should tell them how to put that truss up there. What I'm suggesting is you should review the site to be assured that it's even feasible at all. We're talking about preliminary design, and when you talk about that preliminary design, you're going to look at concepts and how might it be installed. Not that you're going to figure the installation procedure, but is it installable? Is there a way to do it? How about looking at a 4 or 5 story structure that has that's steel inside and has a masonry outside? In today's environment, today's skills, today's constraints, how do you build that building? The steel guy is going to be in, out, in, out, in, out, in, out, while that masonry is being built on the outside. It is certainly not cost effective. There needs to be another process with regard to that. That doesn't mean the system is incorrect, doesn't mean it doesn't work. We're looking at collaboration with industry experts, as I said, and also the owner, so he's aware, and that you want to make sure that you kind of review. You do have constructability reviews, but the constructability reviews are a review of your constructability process and not a constructability review of the documents after 6 or 7 or 8 or 9 weeks. We evaluate the client's needs, and we have a team. Now, the team is not your typical model that we have of your line. He's in charge and stick down to him, and he goes out and 4 or 5 sits and goes down and keep all the way down. So you're down here at the end of the 3rd line. You have to go through the architect. He has to go through the owner's construction manager back to the owner's representative owner, it goes back to the owner. What we're indicating that we want to have, excuse me, I'm sorry, hit the wrong button. We want to say that this is a joint process, that we have input from everyone with the owner coordination with regard to this. Now, the owner doesn't have to coordinate it so much, but the owner is the focus because he's the guy with the money and he has the issue that he wants. And you really want to keep him happy because hopefully he'll build something in the future and call you back. I mentioned earlier the design relationships. Construction Industry Institute indicated that the nature of competitive practices promotes short-term adversarial relationships among the contractors. And that's what we're dealing with your scenario and your design and concern relationships. And we have to start breaking those down, and you're only going to do that through a mutual individual trust and sharing of information looking at the issues, talking about the staging site, what kind of equipment and site work is there, what can be done. We can look at the preliminary issues. We evaluate geometry, load carrying characteristics, what's the lateral load resisting system. As a matter of fact, we had a conversation yesterday and Tuesday with the Education Committee, and I suggested that does anybody have an issue here in the universities of teaching lateral load path? Many of you have gotten into structures, and I'm sure you've seen them, where we try to find where is the load path. Is there a load path? The Kota standard practice asks you to define the lateral load path, load resisting system on the documents. That's not there to trick you. That's not even there to test you whether you know what it is. The primary focus of that is for the contractor to have some concept on where is the natural lateral stability in that structure that you assume that you have, because they have to provide stability while they're building it. So if they know what your lateral load resisting system is, then they may be able to use it, and then again they may not. But if the lateral load resistance system ends up being reinforced concrete masonry that's going to be installed 6 weeks after your structure is in place, then there is some major lateral support required. So it's a matter of cost and schedule. Conceptual erection. We want to look at erection concepts. We're going to look at establishing member constraints that are controlled by the construction loading, define maximum PICs, investigate equipment availability. One of the issues or things I find here on large structures that designers will look at a structure, maybe it's 150, maybe it's 200-foot span, etc., and they'll come and say, okay, we're looking at you, we've designed it so that you will shore it at the quarter points. So that means I have to put up 3 shores. Now that truss is designed to span 150, 200 feet. So granted, I can have a shore out at 50 feet. But what I can do with 50 feet, I can cantilever off that another 35 or 40. And then I can do the same thing on the other side and close it and only use 2 shoring towers. Now if those shoring towers are 120 foot tall, that's a 12-story building. So if I only have to build 2 and not 3, I have a lot more time, less cost, better schedule. So understand your decisions. We talk about impacting dollars and maybe inconvenience. What it really generates is that it's cost and schedule that you impact. And so those sorts of elements, I find that at times we go back in and redesign, or have to change some of the bottom members or change some of the diagonal members because we're going to cantilever that 200-foot truss. And the approval process to get that changed so that we can only use 2 shoring towers versus 3 is, well, it takes time that probably is not necessary to take time. And I'm suggesting that some of those things might be suggested in you doing it. And even the other situations is that you very likely may be able to take this 200-foot truss and break it down into a 120-foot section and an 80-foot section and use 1 shoring tower at about 85 feet, 80 feet. Let it cantilever 40 and close with the 80 foot on this side, as long as the truss is in the air. However, what happens is that now there's a difference in the dead load distribution. And one of the largest things that we as construction engineering have conversations with engineers on is that the structure that you design is a 100% installed complete structure when you put your dead load on it. It's not built that way. It's built one piece at a time, and the dead load goes where it's naturally going to go. And it's very, very, very difficult to move that. So when I have large structures, unique structures, curved structures, hangars, stadiums, arenas, your dead load distribution that you assumed in the design is not what's in the field. So there are There is information there that needs to be discussed and talked about and can be assumed early on. So those are things I would say that someone in the construction area can bring that knowledge up. Yes, sir.
So when you're dealing with these kind of trusses, they're not tension members, you're dealing with thrust loads that can affect the deflection of the primary structure, and you know, your overall profiles get all messed up. You've got a lot of things that, you know, the masonry built, you know, 150 feet away makes a big difference on how the rest of the building performs.
Correct.
And those thrust loads have a big difference on how the truss is designed with respect to, you know, 100-foot thrust versus let it slide for a little while. You know, your foot connections when you're releasing it makes a huge difference.
That's correct.
On the truss.
Yes.
So,
Well, one of the things we find is the fact that we oftentimes do not have enough information from the designer with regard to what elevations are you expecting the final structure to be in. And in fact, from that point of view, that becomes a major discussion. We just completed the installation for the Kansas City Performing Arts Center. I don't think there's a vertical member in that structure. It has curves going every which way but loose. And we are bringing intersecting structures in from left side and right side that are supported off a 220-foot long box truss that's going across. And what we're indicating is that depending on how we install that box truss, the elevation at the center will vary plus or minus 3/4 of an inch, just based on the way we put it up. So where do you want it? Okay, well, when you take the whole model and it's all complete, and then you put the load on it, well, the load goes very neatly with the geometry. But when you're erecting it, it doesn't really go there. So we had many, many conversations back and forth with the engineer in order to establish an erection procedure where we did jacking, where we had to change member lengths, where we had to do it in order to establish some reasonable location. The other thing I will tell you is that you'll take that structure, and in the specifications it says, this structure shall be built to AISC tolerances. And I will tell you, those tolerances do not apply to that building. We don't have tolerances in AISC that tells you where the center of a truss should be. It only tells you where the work point should be at the columns, where the floor height should be, where the floor line is. There's nothing where that is in the middle. It has some conversations with regard to sweep, etc. But if you want an elevation there, you need it to tell them. Okay? Now what happens when you do that is what's applied is camber. Not a good idea. Why? Read the tolerances for camber. -0 plus 1/2. And there's no guarantee that the camber that you're calling for will be in the field when it gets there. So if you're looking for elevations of steel in the field, you need to define it as an elevation. This is the elevation where we want it. This is the tolerance of that elevation, because there's not a tolerance. So that then you can determine and make that decision as to what it is. Camber, as defined in the code, is only there to provide means to compensate for the deflection of the beam when concrete is placed on it. That's it. So that you have a 5.5-inch slab doesn't become a 7-inch slab because the beam deflected 2 inches, so you put 2 inches of camber in it and then you pour your concrete. Now what we have is, that certainly is another eye as to how do you pour the concrete, where do you pour the concrete, how do you straighten the concrete. So I will tell you that camber is a very imprecise means, and it's strictly an opportunity to reduce the amount of concrete that will be placed, but it is not a means of establishing an elevation. It is not a means of establishing an elevation. I can't say that enough. If you have a critical elevation, define it. Tell me what it needs to be, and then the contractor is going to tell you what that's going to cost you to get there. Now, I have a response from an engineer when I told this to him once before on a very, very, very elevation-sensitive structure. And his response to me was, well, if I put that note on the drawings, that'll increase the cost. Yeah, it will. Okay? It will. I agree. It will. But if you need a precise camber scenario, a precise elevation, camber is not the means to do it. Okay? When we were looking at constructability from the whole philosophy and concept, the issue is that we're bringing information into the knowledge, into the process. And during the concept and feasibility study time, when we're working the project out, those ideas are practically 100% usable and basically cost us nothing at that point in time. As we move along the chart, our ability to influence drops dramatically, because once you start building the box and you have the walls up, you're now locked into whatever that decision is. You're locked into it. Likewise, or conversely, the cost associated with that knowledge and how it impacts the actual dollars spent is I get this knowledge for practically nothing, for practically no cost. When I start generating on this line, and I'm starting making my changes down in here, I'm impacting the cost significantly. Steel design considerations. You've heard these before. I'll probably repeat them again. You want to maximize the shop work and minimize field. You want to avoid multiple component sizes. What does that mean? Well, should all the purlins be 14 at 30s? But no, I got a couple of 34s, so I'll make them all 34s because that makes it cheaper. No, that's not what it says. What we're looking to try to do is on a given floor system, that you don't want a 14 here and a 16 there and a 12 there and a 14 there and a 16 there. You don't want to do that if you can help. We'd like to have uniform bays and columns. But we can take non-uniform, but understand cost and schedule. Efficient framing schemes. 30 by 30 bay for an office building, 30 by 40, 25 by 40, 30 by 25, in that range. It's the least cost system. But that doesn't mean you can't do a 40 by 40. Doesn't mean you can't do a 40 by 60. It says cost and schedule with regard to your decisions. You want to maximize column lengths. What I've seen, which is kind of strange, but when you generally put that in RAM or put in some of these models and they start dumping out column sizes, they'll give you a column size every floor. Well, there's no benefit in all those column splices. I will tell you that. There's no benefit. But however, when we're talking maximize column length, you need to be aware of your local, where this is being built, constructed, and what the local union rules are. Because there are places in the country where you cannot install a 3-story column. And other places in the country you don't want to install a 3-story column because you have guarding safety net requirements when someone gets above 30 feet. So if that is something you need to be aware of, ask the questions, get the right answers. Shop and field tolerances for adjoining components. We like to put steel to concrete cores. The two tolerances between those two, it's like mixing vinegar and oil. They aren't the same. Is the embed going to be where you want it to be? No. I guarantee it's not. Make it larger. Make that bed a couple inches larger all the way around. At least it'll probably fix 50 or 75% of the ones that don't get in the right location. I don't know if you can see this. I hope you can see this picture. From anybody been in Chicago and been to Millennium Park? Well, that's what the steel looked like before from the backside. That's what it looks like from the backside. This is what it looks like at night when it's lit up, all stainless. This is a Frank Gehry project. We had an interesting part we played in this one. This model, was primarily designed by Skidmore, Owens & Merrill. They used 3D modeling to put this project together. There was an exterior contract for the skin. The original contract documents indicated that the structural steel frame would be installed. The key points would be surveyed, and then the skin connections would be developed. The general contractor in eminent wisdom decided that, well, the steel has their model for building a structure, so I'll just give the same model to the skin and tell the skin people, you need to put the skin on that model. Well, when you build this structure out in the field, and this picture really doesn't do it justice, this structure is extremely complicated, has truss support systems and diagonals going many different directions. And when it was finally built, and it was built as close as you could build within, quote, AISC tolerances, we have joints there that are 12 inches away from the model space because of deflection, because of temperature, because of construction tolerances. Well, guess what? The skin was 12 inches away from where it was attached to, so there was a major contest here as to who pays for what and what is there. But essentially what I'm indicating on there is that the tolerances for that, it's indicated that the fabrication installation tolerances shall be per AISC. Well, AISC, if you look in the front of it, it's called the Specification and Code for Steel Buildings. That means vertical columns and horizontal floors, and we're going to pick the nodes. And this structure is nothing but nodes. It's nodes every which way but loose. The structure finally got built, got put together. It's very attractive. It's very unique. But the way the contractor decided to do this, because he felt that would save schedule time, took no account at all into the geometry of the structure and the dead load deflection and deformation of the structure. Efficiency connections. How many times has the model of your program kicked out a W14 or a W36 of framing into an 8-inch member, because that 8-inch member only spans 6 feet between columns and obviously needed 24 will work. And those sneak out into your design drawings. I would say you want to take a look at those things. You want to make sure that you want to look at the framing and make deeper members into shallower members. You want to avoid that. You want to avoid web connections into shallow, wide flange columns. Columns, in other words, I've seen one of the presentations where columns can vary on this from 6 inches up to 14 inches. The only time you want a 6-inch column is if you're going over top of it. You certainly don't want to frame into it. So we don't want to frame into 8s. You don't really want to frame into 10s. Some 12s are a problem. So essentially, 14-inch are what column sections are. If you're doing 12-inch members, then you want to make sure that your beams, flange width, will fit inside that hole between the flanges. Because if it don't, they have to be coped out. Cost, schedule. Cost. Single connection. 1, 2, 3, 4, 5, 6 bolts. 52 kips, 1-inch diameter A325 bolts. Let's say I consider snug tight. Threads excluded from the shear plane. 3 bolts, $21. Threads in the shear plane. 4 bolts, $28. But I'm not sure about snug bolts. You know, those bolts, those loads might get light. Those nuts might come off. Snug tight. Full force of an iron worker with a spud wrench. Spud wrench is 18 inches long. I know an iron worker that can take a 3/4 inch A325 bolt and break it with a spud wrench. So when we're talking snug tight, trust me, you do not want your fingers in those layers when he tightens that bolt down. So backing off is not going to happen. But at that point in time, I've got two choices: 3 bolts, 4 bolts, $21, $28. But you would like to have them pre-tensioned. And I'm not sure what I understand about that. I have a story for pre-tensioned here in 1 minute. I'll give you that. But anyway, same bolts. But now they cost me $31.50 because I have to tighten them. And if I do the 4 bolts, I'm up to $38. Okay? Let me tell you about pretension before I go further. I got a contractor call. He calls me up and he says, all the bolts on project's up and everything's been rejected. He said, I ordered the bolts, I put them in, and they're telling me they're rejected. I said, well, what's rejected? He said, well, they say I have to tighten them. He said, I ordered pre-tensioned bolts. I said, I think you better go tighten the bolts. Right? But, yes, I got that. I'm not making that up. But let's say you want you are a fan of friction bolts. Slip critical. That joint's going to cost you $68. So understand that little decision you make, slug tight, included, excluded, pretensioned, cost, schedule. In this particular case, we're talking twice the bolts. That's twice the man hours to install, twice the man hours to torque, twice the detailing in the field, twice the detailing in the shop, twice as many holes to drill. Because there's more holes to drill, the shear plate is longer, there's more weld to put in place, cost and schedule. You want to avoid build-up shapes whenever possible. And why is that? Because it's man hours. We'd like you to use AISC tabled connections. AISC does not have what are called standard connections, if you will. Since they're published in the book, they become somewhat of a standard, but you have single shears, and you have single angles, and you have double angles, and you have seated connections, and you have stiffened seated connections, and you have extended shear. So we have a whole bunch of tables, but those are the connections they would like you to use. Minimize bolt diameters and grades, and one of the reasons for doing that is to keep the inventory in the field to a minimum. These things come in kegs. These kegs are heavy, I guess that's a good expression, and they have to keep and in most cases the bolts and nuts become separated unless the contractor buys them together assembled. When they buy them assembled, there are less bolts in the keg than there are if the kegs just come. So what you're trying to do is to try to say you have 1-inch A490 bolts, and then maybe you use 3/4 or 7/8 A325s. That's kind of what they like to try to do. You can tell from the head as to whether it's a different bolt. You vary the size. The object is to simplify in the field. So when the raising gang goes up, he doesn't have 3/4, 7/8, 1-inch, A325, A490 bolts in this bolt bag he wears around his belt. When he goes up to the joint, he's got 1-inch A490s. That's all he needs. So trying to do that, you're looking at joints. So when you get to a joint, you'd like everything in that big joint to be the same if possible. AISC has many design guides. As of the fact that this is number 23, I would suggest that you look at them. There's a generate amount of information in these with regard to design procedures, recommendations, details, detailing, etc. They are very, very valuable. We need to, one of the things you may not, probably certainly doesn't come into your design process, but in fact it is a relevant issue. Do you physically have the adequate clearances in the details that you're drawing to physically make that joint? Can you get there? Can that be a proper joint? Question I had in consulting on a project in New York, I'm looking at the drawings and I see columns that are 14 at 7/30s. Diagonals coming in are 14s at 550. Loads are in the 2,000 to 3,000 kips. Floor to floor height in that area is like 12 feet in this particular area. And we have kind of the diagonals are somewhat of a chevron joint. And I ask, has anybody drawn this joint up? Well, yeah, it's right here. No, that's a stick and a stick and a stick, and it fits. Have you drawn it up to scale? I said, because I think when you draw it up, you're going to find that the gusset plates are touching. Matter of fact, they may even be overlapping. So 2 weeks later, I came back, and they had drawn it up to an 1/8 and 12 scale. I said, I'm sorry. No. You need to draw this up to 3/4 and 12, 1 and 12, but you need to see it. You need to feel it. And then you need to put on there what size that gusset plate is physically going to be, because you're asking somebody to do that. And they're saying, well, that's the fabricator's responsibility. I said, I'm sorry, but I understand that you've got a design and you're generating this process and you're sizing all the members, and now you're going to take the whole process of this structure doing what it's supposed to do, and you're going to assign it to this fabricator to make sure this thing works. And guess what? There's going to be 6 or 7 fabricators bidding this project. I said, you need to level the field. You need to tell them what you expect. Because what I find in experience is that in most cases, they haven't drawn it up. They don't have an idea of how this is going to be done. And in some cases, what we find is because it's a bolted detail, we have a net section problem. But the analysis program doesn't check net section for the tension members. It just tells you what size that member has to be based on its gross area. Guess what? Those 550 diagonals are too small. So who puts the money in? Who puts the time in? And when does it go in? Well, generally speaking, it would get bid with a 550, and then you would have an extra claim within the first week, because we have to change those to 730s, and since you've notified us late, we can't get them. There'll have to be a built-up section. So I'm indicating to you, I think it's wise to have an idea what that detail is, and can you physically make it. As we talked briefly about camber, I will repeat again, camber is a very imprecise means to adjust for dead weight deflection due to concrete, period. Does not establish elevation. All you'll get is headaches and heartaches from that. I would say I would make it your policy office practice to utilize the knowledge that's available in the industry, particularly the design guides, but also individuals in the industry who have been in the industry. Maybe they are retired, maybe they're a contract you have a good relationship with, maybe they're part of their local institute. I know that none of those requests will ever go unanswered. Joint details. You're going to consider joint and geometry, develop preliminary scale drawings. Scale, and I probably should have in there. I should say 3/4 and 12, not 1/8 and 12, sorry. And you want to look at the actual assembly, and don't put down what you think you want it to look like, put down what it's actually going to look like. You want to maximize shop work, and I've repeated this, and then again, minimize field work, but we want to consider erection stability, shipping constraints, and member widths and lengths. Now, why is that critical? Okay? Well, let's say most of our programs have the ability to do least weight design. And they will give me top chords of members that are like pieces of spaghetti. I have to ship that piece, I have to lift it, I have to install it, and I have to maintain stability of it until whatever final system for stability is there. All of those elements are cost and schedule, and probably exceed the cost of making that particular cord 10 pounds heavier. I know you get beaten up by contractors and CMs for your pounds per square foot. I understand that. You need to stand on your own 2 feet and tell them you know what you need to know. For instance, just as a general rule of assembly, if you're looking at a piece, if you take its width, whatever it be, top flange of a girder, top flange of a truss, the width of that member, 12 inches, 14 inches, if you divide that into the length of that member in inches, okay, and if the number is 80 or less, I can set that member and it will stay there and it will be stable. If it's between 80 and 100, I need to perform an analysis to determine whether it has lateral stability. And if it's over 100, the chances of it collapsing after you let go of it are very high, which means that I need to do, as an erector, I need to provide stability. I need to provide lateral cables. I need to provide some sort of thing. I need to put angel wings up there as a bracing system. I can do other sorts of elements, but all of those are cost and schedule. And that top chord, which is the magic number, L over B equal to 80 or less, provides a lot, is good. 80 to 100 is passable. Over 100, just don't do it. Cost is too great to the whole project. However, I will tell you is that cost is invisible, because everybody will have it in their price, and it will not be reflected in your tonnage or in your cost per ton or in your cost per square foot. It will be over the budget, I will guarantee you. This is a joint as shown on the design drawings of a major structure in New York City. We are talking a horizontal load here of approximately 800 kips, horizontal load here of over 2,000, a vertical shear force at this point, and approximately 2,200 kips going into the shear wall. The member shapes are shown. What they basically amount to is this is a plate, this is a plate, structural member, and there is the column we're framing to. It's a 14 at 90, buried in a 24-inch square shear wall. Question: how does the load get out? How's that 2,178 kips get into the shear wall? Answer: it worked in the model. Well, what you're seeing here was not on the design drawings. That's what finally was designed to generate in plan, in section, transferring that force in there. And from a 3D view, that's what that plan on the drawing was, not drawn up. Issue here, infringement on the elevator. This situation here had to completely redo the reinforcing in the shear wall in order to transfer all of this shear force, axial force, out through these studs into hairpin reinforcing into that whole shear wall system. Response: it worked in the model. You need to draw these things up. You need to see what the contractor is going to be seeing so that your decisions as to what you're asking him to do are more realistic. The ASC Code of Standard Practice. How does this impact constructability? It impacts it from the point of view that what the Code of Standard Practice indicates to you is that is the product that will be delivered to the site and installed if you do not indicate anything differently on your documents. So we're talking about tolerances, special procedures, detail requirements, elevation requirements, special procedures that are necessary. Maybe you need to have part of your project preloaded. We have maybe the bottom cord of the trusses are catenary trusses made out of cables. They need to be preloaded. All of that stuff needs to be defined because it's not covered in the code. So I would say to you, I would like you to be aware of what's in there, not because it's a threat, but because it's information, and that if your structure needs something else in order to do what you want it to do, then you need to define that. It's only That's the only issue I would bring up to you. We're talking about, we're saying that you need to define those requirements, and including the lateral load-resisting system, so that there is a means to do and develop the erection sequence and procedure. So with this, what I would like to do is introduce Chad Fox. Chad will walk us through Chapter 4 on steel framing and some of the issues and special cases, studies that we have generated. Thank you. Chad?
And like Dave said, I'm going to be getting into Chapter 4 of the Constructability Design Guide. And what we're going to do is go through some examples and some case studies to see where constructability can really help us reduce both cost and schedule. Dave went over this already a little bit. There's a pretty common misconception that the cost of our steel building is related directly to tonnage. And really there's a lot of other things that go into our cost and that can add to schedule. Tonnage is there, but also shapes. Does our design, does it include every single shape that's in our steel manual, or are we able to group it into subsets and use shapes that are readily available to our fabricators? The same with the material grade. Have we specified material grade correctly, and are we sure that a fabricator can get a hold of it? Detailing costs. Detailing really, it's a lot more a function of the number of pieces than it is tonnage, and also the amount of repetition that's built into your structure. Fabrication, again, tonnage is a part of it, but a lot of it is the number of pieces again, and the number of the amount of repetition built into the structure, both in member sizes and then connection layouts. The guy working in the shop, he's no different than you or I, as far as when we do a calculation. The more times that we do it, the easier it is, the faster we can do it, the less chance that we're going to make a mistake. It's the same with the guy in the shop. Shipping, it's a function of your tonnage and also the number of pieces that you need to ship. And then erection, have we done everything that we could do to move our man hours from the field and into the shop? Because that's going to be your most expensive man hours. And then beyond man hours, there's also a cost associated with the overhead, depending on your schedule length. There's the cost it takes to carry insurance over the length of a project. There's administrative costs. First study we're going to take a look at, this was actually put together by a friend of ours, Bill Treharn, with Midwest Steel. They're rectors out of Detroit. And what Bill decided to do was take 4 different types of lateral systems, and all else being equal, what is the associated cost and schedule for each of those. So the first one he took a look at was a Chevron Bracing system, just your basic double angle, field bolted, and you can see he's neglected the interior of the building. We just assumed that your diaphragm can carry all of the lateral load to the systems on the exterior walls. Second system, tension X bracing, same thing, double angle, bolted in the field. And then we also took a look at a couple moment frames. The first one, field bolted end plate moment frame, and you can see with the forces it required stiffeners in the columns. And then the final one is a field welded moment frame. And so this chart really gets into material and also time. It's really a breakdown for each one of those systems, what it's going to take to build that. And so you can, starting from the top, you can see there with the brace frames, we've got a few more pieces. Then when we get down to weight, there's considerable more weight and tonnage associated with either of the moment frame options, from upsizing your girders and your columns so that you can still meet the strength and drift requirements. Bolting, you can see it's going to take the most amount of bolts to do the field weld or the field bolted moment frame. And then shop labor per ton. You can see either of the moment options. With the field bolted, there's a lot of time associated with putting those end plates on, getting the bolt holes, and then the time in the shop. Oh, also the stiffeners that were included in the columns. There's a lot of shop labor there. And then also with the field welded, you've got your material preparation for those field welds. And then also when field labor per tonnage, for when it's in the field, you can see, not surprisingly, it takes the most amount of field labor for the field welded moment frame. Cranes on site, erecting the end plate moment frames, it takes a little bit longer. They're a little bit more difficult to fit. Man lifts, it's 3-man lifts times 2 weeks, or 3-man lifts for 3 weeks for the moment frame options. That has to do with the follow-up bolting or the follow-up welding for either of those moment options. Shop detail drawings, and then installation schedule, you can see it's going to take longer with either of the moment options. And when we actually take a look and break this down by price, you can run down that list. Material is directly linear to tonnage in this case, since we don't have any crazy shapes. It's just wide flange and angles. Detailing, slightly more for the detailing of the braces. And here you can see considerable difference between those options as far as the shop and field labor. Equipment rental, inspection, shipping, again a function of your tonnage and amount of pieces. And so when you get down to the end, the total cost, you can see the total cost either of the bracing systems is much cheaper than either of the field, either of the moment frame systems. And so each structure is going to be different, but that's a fairly good rule of thumb. Your bracing systems are usually going to be cheaper.
So I can read those numbers with that, like $1,900 for bracing.
Which are you, the total?
Yeah.
Okay, the total cost per ton. It's about $1,900 per ton for both of the bracing systems, and about $2,100 per ton for both of the moment options. Next one.
The question would be, those numbers are a few years old, but the difference would be is that you find that within the general contracting industry, and primarily with most of the design industry, your records and things that you keep are based on price per ton. And you can see in these systems up here, the price per ton between was $1,900 on one end and $2,100 on the other end. So the variations you have for what price per ton is, there's not much variation there. And it's not a very accurate meter. The meter is dollars per square foot. The difference is $8.83 on the one side, $13.30 on the other side. The difference in cost per square foot of the structure. So I would like you to kind of, whenever you get the feeling that you want to consider structural steel on price per ton, I'd like you to lay down until that feeling goes away. I would like you to understand that there are so many elements to pricing steel. There are so many elements that the only way it gets priced per ton is that after the fabricated erectors price it, they have a price and divide it by the ton. That's what we do, because that's what somebody wants to do. But it is not a very good metric for determining the economy of framing, or even making a decision as to whether the structure should be concrete or steel, or masonry or timber. You need to look at dollars per square foot. And that was really the focus of this particular thing, was to really show where the elements are. The material cost cost only varies by, what, $40,000, $50,000 between one to the other. But yet we have, and we actually have more money in detailing on the details for the angle bracing than we have for the moment connection. But everything else balloons. Give $120,000 extra in shop and field labor. So the cost of schedule and material cost is a small part of those numbers.
The next study we're going to take a look at is a typical horizontal bracing system for an industrial building. Trusses spanning about 160 feet, and this system would be designed based upon least weight. It's a tension-based system. So by the nature of the system, we're going to have long, slender elements for our bracing members. But even though this is the least weight, there's some problems associated. There's some constructability problems associated with this system. You can see right there with the long span of the braces and being so slender, there's a good possibility that they're going to need a support at midspan. Some type of hanger rod to the purlin above. The problem with this is to install that hanger rod, you first need the purlin above to be installed. So it really creates a problem as far as your sequencing your steel erection. The second problem that you can see, we've got a lot of members framing into that one node. And when you actually blow it up and take a look at it, there's a lot of work involved here. There's a lot of work involved with the detailing, fabrication, and then the erection. The gusset plates, they'd have to come out either on their own or on the braces. They wouldn't be able to come out on the truss members themselves. So there's a lot of work associated with that node. One option that's a little bit better is if you allow some flexibility in your work line, and you're able to move it down so that your connection material can be located on the bottom of the flanges of the truss cords. There's still a lot of work here, but it's less work than the detail before. Oh, and one other thing, for these braces to be erected, first the trusses are going to have to be up. And when the trusses are up, it creates a really stiff node. So if you bring the braces in and your bolt holes don't quite line up, there's a lot of work involved with moving that column so that you can get your braces to fit. So an alternate system that we can take a look at is this diamond bracing system. And this one wouldn't be as light. It would be more weight. And you've actually got a few more members because you have 4 braces per bay. But there's some advantages with using this system. We get into, well, first of all, there's no more, we've completely eliminated the need for any hanger rod. So our sequencing, it's not being controlled by that. And these braces can be erected from above. When you take a look at the truss node, we've really cleaned it up. It's about as simple as you can get for erecting a truss. And then when we take a look at where our braces are framing in, now we're framing into the interior of our truss member. We just have the braces there. There's no more truss connections. This is easy to detail. This is easy to fabricate. And then with this type of a detail, we can actually bring the connection material out. As you can see, the welds, the connection material is on the truss itself. So it's fairly simple. You bring the brace in, you set it down, bolt it up. And also, when I talked about the stiffness of that previous node, now if we have to adjust somewhat, our bolts don't line up, we're into the weak axis of a truss cord. It's going to be a lot easier to maneuver that. And kind of a personal story, I had a pretty unique opportunity this last summer presented to me, and what it was is I, through one of our local unions, I actually spent a week training as an ironworker apprentice. And so it was myself and 5 other ironworkers that were in training. And what we did for this week is we actually erected a 3-story building from top to bottom. And so we each took turns going through each of the positions as an iron worker, shaking out, hooking on, and then connecting. And when you're connecting, you're actually the person up in the air connecting the steel. And so it was my turn to be the connector, and I don't know if you've ever seen it before, but that was the first time I'd seen it. One of the tricks of the trade, as you can see here, is if they don't have any connection material or any other beams framing in, what they'll do is they'll take their spud wrench and they put it in a bolt hole, and they use that to stand on. And so it's my turn to connect, and I'm up there. I've got one foot on the spud wrench, the other leg's wrapped around the column. I've got one hand signaling in the crane, and then the other hand bringing in the material. And while I'm up there, I realize a couple things. The first thing I realize is I probably should have brought a change of underwear, because when all you have to stand on is a spud wrench, 30 feet might as well be 300 feet. And the second thing I really realize is the decisions that I make, the choices that I make, whether I'm the SER or the specialty structural engineer, but those choices that I make have a direct impact on the safety and well-being of another person. Because their jobs, it's difficult and it's dangerous. But aside from compassion for our fellow man, there's a lot of time, and not just time, but there's a lot of risk associated with trying to construct a building with details that are difficult. And that time and that risk, it's going to make its way back to the owner in the form of a cost. First case study, we're going to look at actual projects that we've worked on. This is Lansing Community College in Lansing, Michigan. And the original design, when it was brought to us, it was a 3-story building with the possibility of a 4th floor in the future. Based upon the design, bid, build, delivery system, the cost of the structural system was coming in at about $2.8 million. Taking a look at the original design, they had used the least weight methodology for designing their floor system. So they ended up with floor beams at 3 foot on center. The metal deck was fairly thin at only 2 inches, and the slab on top of that was thin also. All of the beams were specified prescriptively as the UDL, 1/2 UDL. You've probably seen before. There wasn't a consistent lateral frame throughout the building. There was multiple cases. And then a lot of the details required field welding in the field. So taking a look at this, there was really some ways that we could use constructability to decrease cost and schedule. And some of those things that we changed, instead of the multiple lateral frames, we just went to field bolted everywhere in both directions. Took out the field welding wherever possible. You just use bolted up connections again, moving your labor, putting your labor as much into the shop and out of the field as possible. There were also some composite columns that were eliminated. They were tubular columns with concrete fill, and this really created a problem with the interdependency of the two trades. Obviously, the concrete needed to be placed before the top framing could be put in, and that created a problem. And then instead of the UDL requirement, we used actual shear loads for the connections. When we look at the revised framing plan, we were able to move the beam centers out to 10-foot spacing, which obviously it increased the slab thickness and increased the metal deck, but it resulted in about 75% fewer beams That's a big decrease in the amount of pieces that you need to install. A close-up of a typical bay. You can see the original design on the left and the redesign on the right. And you can notice the sizes increased, but they didn't increase relative to their tributary area. And that was because with the increase in the slab thickness, we were able to get a much more efficient use of the composite beam action. So in total, we removed 700 members, which computes to 1,400 fewer connections. That's a lot of field time taken out there. Reduced the amount of shear studs, and then in this case, we actually were able to take some steel tonnage out of the building. And in the end, for $200,000 less than the original design, we were able to include the fourth floor, and even with the time taken for the redesign, it was still completed on schedule. And this is a breakdown of the two buildings, the original design on the left and the redesign on the right. You can see the decrease in cost and also the decrease in schedule, and you can notice that both the cost and schedule include the time used for the value engineering redesign. Second case study we're going to take a look at is this is a manufacturing building, I believe in Georgia. And this building was kind of unique. It had five crane runways throughout the building, and the cranes that they selected, they needed to be supported every 25 feet. So the original design just had trusses at every 25 feet. And five lines of sway frames throughout the building. What was interesting about this is you took a look at the trusses, and since the trusses were carrying, I believe the trusses on the left were carrying 3 crane runways, each one of those trusses needed to be designed with the assumption that that crane could be fully loaded directly below that truss. And so when you took a look at those trusses, 60% of the load that was contributing to their design was due to those cranes. So what we ended up doing is moving the trusses from every 25 feet to every 50 feet, and even though they have twice as much tributary area, the crane loading for each one is still the same. And so we cut in half the amount of trusses, but each truss maybe went up 10 to 20% in weight. And then to take care of the 25-foot requirement of supporting the crane runways, each sway frame actually ran below where the crane runway needed to be supported. And then in the original design, you can see the purple columns are actually gravity columns. So with the trusses at 25 feet, we needed jack trusses to carry the load to the gravity columns, and we were able to eliminate those, since now at 50 feet all of our trusses span directly to a gravity column. It's a breakdown of the base bid and the alternate bid as far as material. You can see there's quite a reduction in material there, and which resulted in a significant amount of savings, close to $1 million cheaper, and we were able to reduce the schedule by 16 weeks, and that the 34 weeks with the redesign actually included the 6 weeks of constructability redesign. The last case study we're going to take a look at, this one's a little bit different. It doesn't involve a redesign. It's the St. Vincent. It's located in Toledo, Ohio. And the owner for this project, about 2 years before starting this one, they had built a hospital with the typical design bid build construction delivery method. And this hospital and that hospital were nearly identical. And the owner was kind of ahead of his time. He thought, if I bring in the design team and all the main contractors in the beginning, I think that I can really reduce cost and reduce schedule. So you saw this slide earlier, and this is what he did. So from the very beginning of the project, everyone was involved. The design team, concrete contractor, steel erector, and the end result was that this hospital was able to be constructed quite a bit cheaper, and there was also a very significant amount in the time it took to construct it. So that's a really good example of how constructability can influence your project if it's involved from the very beginning. I think that's it. Dave, did you have anything that you wanted to add?
Thank you, Chad. Any questions for Chad or I? His comments?
I have one question.
Sure.
On the first presentation, you said minimize composite construction. Was that strictly with respect to the columns?
No. By the thinking of composite construction, what we were really talking about is trying to marry two systems where we have concrete core, steel framing to it, or we have masonry bearing providing the lateral stability for the structural steel. All those elements are cost and schedule. They may, in fact, unto themselves be under first cost basis, may be the least cost way to do something, but when we start to integrate them, if they're not integratable in the design process, then they become a cost and a schedule impact. And it's not a local decision, in other words, not a national decision. Pardon. It's a local decision with regard to what is good for your area. So if you decide that what's good in Florida, you're going to take that to Wisconsin, it's probably not a good idea. Palm trees don't grow well there. It's just a matter of know your area, know your joints, know your clients, know your customers, and make that decision. But generally speaking, it's something that you probably want to look at rather than trying to mesh those systems.
So you're talking strictly about the floor system and the concrete slab. The issue of whether you can use composite beam converter versus non-composite.
No, it's not. We're not talking about the floor systems. Correct. Yes. Thank you for clarification of that. Any other questions? Yes, sir.
Well, you were discussing the last one case study where the crane rails and stuff, but you have truss length versus weight, and you have an erection cost issue. You know, once you need to use spreader beam, once you need a certain size crane on a site, you have a lot of flexibility. So if you spread out those trusses, you can end up saving costs. But if you spread them out where they get heavy enough, all of a sudden now you're bringing in an additional crane or a separate method to work with them. And, you know, some of your the idea that you were talking about, 85%, 15%, cantilever it out. You start to get into some of those issues too, where your fix and what you're capable of doing, you have to address that.
Yes.
Not everybody thinks about that sort of thing.
It doesn't happen. This particular project was kind of unique. These were underhung cranes, as Chad was indicating, and when you put them there, this is in Georgia. It doesn't have it. It's a code-applicated roof load, live load, so when you move it from 25 feet to 50 feet, you pick up another 10 pounds a square foot for 25 feet. I mean, it was no really big deal, but each truss had to carry it. So we gave a presentation on this, this design in particular. The owner, we took out 800 and some tons out of this project. The owner's response to this, Lockheed's response to this to the contractor is, there is no way you took 835 tons out of my structure and are giving me the same structure. The original engineer, to his credit, told the owner, stood up in the meeting and said, actually, he's not giving you the same structure. His structure is stiffer. We moved the bracing around and it's much more efficient, even though we took the excess tonnage out of the roof. But we added, if we go through that breakdown, what you'll see here is that there's significant additional bracing members. 72 in the original structure, 172 in the final structure, bottom chord bracing. So we actually enhanced the lateral load distribution system, making the whole system much stiffer. So We gave a presentation to the original designers of this in their office. And the only question we got at the end of the meeting was, what is your phone number? We don't think that way. And and I'm saying to you, I understand. I tell you that I started working at American Bridge, and my responsibility when I started to work there after 2 years in the drafting room was to review every building between the Pennsylvania state line and the Rocky Mountains, whether it be steel or concrete. And my responsibility was to find another way to build it, to do an alternate option, find cost savings. I was working with U.S. Steel Marketing out of American Bridge's office in Chicago. I did that for 3.5 years. So it is very difficult for me to look at a set of drawings without saying to myself, how can I do this better? So that's part of the process. That's just the way I think.
Where I'm getting on that is there were some of these big box buildings, you know, people were always so tuned to the 55 foot, 45 foot, you know, those kind of bay sizes, those are the least cost tonnage. But in the end, you're going to need a certain size crane, you're going to need a certain size or methodology to your erection. But if you push that out to 80, 90, 100 feet, it's the same process. And it's, you know, you're cutting your erection time, you know, down.
You're cutting those.
With Atlanta, you can't ship the piece. But if you're dealing with some of these other states that have the room, that have the shipability, you might as well send a big piece.
And what I'm indicating is what you're saying is that that's information that is normally not in the designer's decision matrix. You haven't been trained to do that. You weren't schooled to do that. And most engineering firms don't do that. They actually feel within those firms is that I have been approving shop drawings and looking at e-sheets for the last 25 years. I know how they build steel. What you don't know is the cost associated with it, because the approval drawings you've been looking at have been the approval drawings that you designed. And so for my feeling is, it's somewhat like incest. I have a bad idea and I'm going to reinforce it. So I encourage outside information, encourage critiquing, encourage construction professionals to talk about it. Even on projects you have right now that are design, bid, build, I would encourage you, after the project's done, invite the contractors in for a meeting and tell them seriously, we want to know where we were, what things could we have done better, what cost you extra things, where they're simple. Try to open up that dialogue. The first time will not be successful. Do a couple times, then they'll know you're serious. But there needs to be a dialogue generated. Okay? Any other questions? The number for this, I will repeat again, S is in Sam, G is in George, 79K. And we're right on time. Thank you very, very much. Appreciate it. Have a great day.